Okay, let's unpack this then. Deep learning models, they get incredibly efficient, right? But what are the hidden costs? What's going on under the hood? Today's deep dive is into this, well, this fascinating world of quantization attacks. You've shared some really interesting, dense research, and our mission really is to pull out the key nuggets so you walk away well-informed about this cutting-edge cybersecurity frontier.
Exactly. And what's really fascinating here, I think, is the core paradox. How the very act of optimizing AI models for efficiency, how that can inadvertently create these profound new security risks. We'll explore why this push for efficiency can sometimes lead to, well, a surprising kind of brittleness.
So why do we even quantize these powerful AI models in the first place? What's the actual driving force?
It's fundamentally about bridging the gap. You have these massive AI models, huge, and then you have practical deployment scenarios. Think tiny mobile phones, embedded systems, edge devices. Quantization shrinks models significantly. I mean, converting from full precision like FP32 down to 8-bit integers, INT8 for instance, that can mean a 4 times reduction in size.
4 times, wow.
Yeah, and maybe over 90% power saving for operations. It also makes the models compatible with low-power hardware that often doesn't even have dedicated floating point units.
Okay, those efficiency gains sound, well, pretty amazing. Hard to argue with that. But where's the catch? What does this mean for security?
Right, here's where it gets really interesting. This optimization, it's fundamentally a lossy transformation. You're losing information. Imagine a smooth decision boundary in a full precision model, like a gentle slope, right? Quantization, because it maps continuous values to a discrete set of integers, it turns that into a jagged sort of staircase-like landscape.
Like a staircase.
Okay.
I can picture that. Jagged edges instead of smooth.
Exactly. So instead of these continuous gradients that many attacks rely on, you suddenly have these cliffs where the model's output just abruptly jumps. Now, this can create what some call a fake sense of robustness because, traditional gradient-based attacks, they often get thwarted by these cliffs.
Because their math expects smoothness.
Precisely. But it opens the door for entirely new attack vectors that exploit these sharp jumps.
Okay, that staircase analogy really helps. And building on that, you mentioned something called precision cascades.
Yeah.
How do they fit in?
Yes, this is critical. Think about small errors. Even a tiny initial quantization error, maybe from an input perturbation. That error can be amplified, sometimes exponentially, as it propagates through the deep network.
Amplified? How so?
Well, each quantized layer, each step, can potentially magnify the deviation from what the full precision model would have done. It can lead to a catastrophic misclassification just from a minor initial nudge, especially in these really deep models. It's like a chain reaction, sort of snowballing.
A tiny push leading to a massive failure down the line.
Okay.
So what kind of new threats are we actually talking about here? Can you give us an example of how this brittleness is exploited?
Yeah. One of the most insidious examples, I think, is the quantization-activated backdoor. This raises a really important question. What if a seemingly benign full-precision model you download maybe from a public hub like Hugging Face? What if it contains a dormant malicious functionality?
Dormant? How?
The attacker trains the model cleverly so that in full precision, the backdoor is completely inactive. It behaves normal. But when you, the user, perform a standard post-training quantization step to make it efficient for your device, that very act of rounding the numbers, it can precisely shift specific model weights across a critical boundary, and that activates the hidden backdoor.
Whoa. So my optimization, the thing I'm doing to make it usable, becomes the attacker's trigger.
Exactly. Your optimization is the trigger. It's a really nasty supply chain risk when you think about it. A digital booby trap, almost.
That is pretty wild. The optimization process itself being the vulnerability. So what can you actually do about this? How do you defend against it?
Well, the key takeaway, the really big shift needed, is that security validation can't just stop at the full precision model anymore. As the research strongly emphasizes, LLMs should be evaluated the way they are deployed.
Meaning you have to test the final quantized model, the one actually running in production.
Absolutely. You have to test that version. It demands a pretty profound shift in how we approach AI security validation. In terms of defenses, there are things like more robust quantization algorithms, Defensive quantization, for example, tries to constrain that error amplification we talked about, or techniques like adaptive or stochastic rounding, basically introducing a bit of controlled randomness or variation in the rounding process to disrupt those very specific weight shifts that attackers rely on to activate backdoors.
Okay, so smarter quantization and testing the final product makes sense. What stands out most to you from this deep dive into quantized AI? For me, it's really a stark reminder, isn't it? That efficiency and security, they often have this deeply intertwined, sometimes really paradoxical relationship.
I agree. And if we connect this to the bigger picture, the security of quantized AI, it's a continuous struggle. It's coevolutionary. The real challenge here, the elephant in the code, if you will, it isn't some static problem you solve once. It's a dynamic, adaptive adversary. They adapt to every new optimization we create. It means we need constant vigilance, constant evolution in our defense strategies. It's an ongoing race